So let T be a linear map defined by Ta x equal to Ax, x being in R4, where A is the matrix given by 1, 2, 3, 1, 3, 6, 9, 1, -2, -4, 1, 4, 4, 8, 5, 8. So what is the question? Determine whether T is 1-to-1 or not. That's what we have. Let me see. Okay, I think I'll get another question. Let me first work out. So we have a linear map which is defined by that formula. They want us to determine whether T is 1-to-1 or not. Now, recall there are two ways. There are two ways of looking at 1-to-1. First of all, in the introduction, we first define what it means for a map to be 1-to-1. Two images that are equal. For two images that are equal, their objects should also be equal. But then we moved from that definition and we came up with a stronger characterization of 1-to-1. If you want to show that something is 1-to-1, simply compute the kernel. Simply compute the kernel. So if the kernel or the null space is 0, then we say that the map is 1-to-1. So what are we going to do here? Recall from the definition of the kernel, okay, we show that, okay, we investigate. This is what we are going to do. We investigate whether kernel of T is 0. If it is 0, then it is 1-to-1. If it is not, we investigate whether kernel of T is 0 or not. If it is 0, then the map is 1-to-1. If it is not 1-to-1. And previously, I think that's where I started from in this session, in today's session. I started by computing the kernel of a transformation. What is the kernel? I think, yeah, the kernel is the zero space. That zero reduction which we are doing. Because fundamentally, this is how it is defined. The range is the column space. The range is the column space, but the kernel is the null space. By definition, kernel of a transformation, here you look at X in R4 such that they are mapped to 0, such that TAX is a 0. So we solve for that. We simply look for the what? The zero space. We equate AX to a 0 and we carry out row reduction. If the answer that we get is a 0, then we shall say that the kernel is. So we carry out row reduction. Let me take this off. What is my matrix? My matrix is so TAX equals 0. TAX equals 0. This should imply that we deal with the matrix 1, 2, 3, 1, 3, 6, 9, 1, negative 2, negative 4, 1, 4, 4, 8, 5, 8. Row reduction. So we fix the first one. Fix the first one, that is 1, 3, negative 2, 4. That. Right. So we fix the first one, then we deal with this other one. For example, to obtain row 2, you see, I'll have, to obtain row 2, I'll have 2 times row 1 minus row 2. 2 times row 1, this will be a 0. This will also be a 0. 2 times row 1, this will also be a 0. Also that is 0. Then for row 3, you can use the 3 times row 1 minus row 3. 3 times row 1 minus row 3, this is a 0. 3 times row 1, 9 minus 9, this is also 0. Negative 6 minus 1, this is a negative 7. Then 12 minus a 5, 12 minus a 5, 12 minus a 5, 12 minus 5, that is 7.
7.
Oh, I did not write this directly. Let's grab this thing up. So this. Also this one down. So this is a 0. This is also a 0. Then for the last one, we can subtract, because this is the last one starts with the 1. Also the upper one starts with the 1. So subtracting R1 minus R4. R1 minus R4, this is a 0. R1, this is a 2. This is a negative 6. This is a negative 4. Like that. So I still reduce further. these rows can be interchanged. They can be interchanged.
Excuse me, sir.
Yes, you excused.
There is a zero somewhere there, as if.
Oh, sorry. Thank you. Zero there. So I can interchange row. Well, I can interchange the second row. I can put it down. I can put the second row down. Then I can put the fourth row in the. I'm going to swap them at once. Hope you will be following. So swapping. Yes, if.
May you explain for me that column vector that 0, 0, 0, where it comes from?
Okay. Row 2. Okay.
Where we get the matrix and then we
Oh, this
the
last column. This last column. Now you look at what I have here. I have TA equals 0. But TA is the matrix A times X. TA is the matrix A times X. So the last column there, which has 0 throughout, is representing this is 0 you are seeing here. It's like we are solving equation. We are solving an equation when it is equal to 0. And the 0 here has to manifest or to appear in terms of a vector. Similarly, if you understand it, still you can row reduce without showing the last column. But the last column, which is representing a 0, shows you that I am solving a system of equations. And since it is a system, it is not one equation, then the zeros will exist in form of a column. So we swap. How am I going to swap this? Shall swap as follows. This remains 1, 3, -2, 4, 0, then 0, 2, -6, -6, -4, 0, then 0, 0, -7, 7, 0, 0, 0, 0. Yeah, that's what I have. I swap. If I swap the rows. And from there, I cannot row reduce further. Okay, if I continue to do what? To manipulate those rows. Remember, the aim of row reducing is to have at least a row where zeros appear. Or the zeros may not appear. At least 3 zeros can appear, then 1. Then for the other entry, it can be a digit, a 5, like that. But when you look at what I have now, if you manipulate this further, you will not reduce it further. You just be moving between 3 rows. Yeah, if I'm to manipulate it further. So that's where I stop. So now in my form, look at what I have now. In my form there, in my resulting matrix, you see that I am operating in R4. First of all, I'm operating in R4. So if I say that X is in R4, I'm operating in R4. If X is in R4, then X has 4 tuples. X has 4 entries. That is X1, X2, X3, and X4. That is if X is in R4. It has 4 entries. So if X is in R4 and it has X1, X2, X3, and X4, from that last row, the coefficient of X1 is not there. The coefficient of x2 is not there. The coefficient of x3 is not there. The coefficient of x4 is not there because all of them, they are zeros. They are zeros throughout. So what shall I do? I'll let x4 be t. If x4 is a t, then look at the third row. Look at the third row. When I look at the third row, I have -7 and 7. So that is the same as -7x3 plus 7x4 equals 0. However, what? However, x4 is a t, so this will be -7x3 plus 7t equals 0. Solving this, -7x3 is equal to -7t. This should imply that if I divide both sides by -7, x3 should also be a t. Then still I proceed to row 2. I proceed to row 2. I proceed to row 2. Row 2 has, look at row 2, we have 2x2 minus 6x3 minus 4x4 equals 0, like that. So this is 2x2 minus 6. What is x3 is t minus 4 x4, which is also t, equals 0. So this is 2x2 minus 10t equals 0, and 2x2 is equal to 10t over 2 over 2, meaning that x2 is 5t. As simple as that. Then we also look at the first column. The first column has x1 plus 3, x2 minus 2x3 minus 2x3 plus 4, x4 equals 0. Then I substitute x1 plus 3 times x2 is 5t minus 2x3 is t plus 4x4 is t equals 0. So this is x1 plus 15t plus 15t minus 2t is equal to 0. So x1 is simply 15. No, this is plus. Sorry, that is plus. That is plus. So x1 is -17t, like that. So what is the key takeaway when you realize that you cannot reduce further, like at this step here, where I obtained this matrix? You can try it out. If you continue manipulating, you realize that three rows will not change. They will remain the same, remain in the same form. That's why I stopped there. Then if you stop at this matrix, then I said that from our definition of the transformation and also the definition of the kernel, you see that we are coming from R4. R4 has 4 entries. So an element in R4 has x1, x2, x3, and x4. So in simple terms, I'm solving for x1, x2, x3, and x4, like that. So when you reach here, this first column is representing x1, second column is representing x2, third column x3, x4. They are coefficients. They are coefficients. That's why I started with the last row, where I have zeros throughout, meaning that x1 is not there, x2 is not there, x3 is not there, x4 is not there. From the last row, therefore, I let x4 be t to deduce others. So if x4 is t, then look at the third row. The third row where we have -7 and the negative, where we have -7 and 7. Having it in mind that the first row is for x1, second row is for x2, third row is for x3. So here I will be having -7 x3 plus 7 x4 equals 0. Then I substitute x4, which was a t. I obtain x3 in terms of a t. Then I do the same for the second row, where I have 2, -6, and -4. Then solve for x2. Then also the same knowledge applies to the first row. So what do I have here? I have x1 is -17t, x2 is 5t, x3 is a t, and x4 is a t. So you see, you realize that the t is common. So this is the same thing as putting the t outside, so that you have -7, 5, -7, 5, 1, 1. Therefore, kernel of t has the vector -7, -17, sorry, 5, -17, 5. I don't know why it's letting me down. Maybe I write up, right side. Kernel of t is equal to -17, 5, 1, 1. And it is not 0. So this should imply that kernel of t is not 0. Kernel of t is not 0, implying that the map, TA is not 1 to 1. It's not 1 to 1. Let me find a question here which you can try out.
Saimo,
Yes, sir.
are those guys still inside there?
They are not there.
Your man, it is very cold here where I am.
Hey, man, me, I feared that coldness.
Why come inside there?
Why not?
Javian.
What is happening in Sankara?
No, there are lectures in all the rooms. I'm here in the garage.
You just repair vehicles.
Get serious, man. I repair whose vehicle?
And
Even
adding fuel.
motorcycles are there.
Andrew.
Add fuel in them.
Andrew. Andrew.
Is Andrew around
This is,
kweli?
this is the
Harriet.
Peru.
Harriet.
Javian.
Andrew, I've got lost.
Javian.
Yes, Omo. Achiro.
The Peru is saying, are you on your abroad?
Tiperu should just come next to me.
Javian.
Hello, Tiperu.
Javian.
Yes.
I'm just checking. Just at home.
Infinix.
At least when you are at home, man.
No longer feeling cold.
Where is Evelyn?
There is with Chile.
Where is Evelyn?
Andrew. And
So take note of the question below, which I think you can easily try out to gauge the level of your comprehension and see whether this concept has been well understood. So what is the question? Yeah, it is. Question. Let T be from R3 to R3B the linear transformation defined by TB x equals bx, x being in R3, where B is equal to B is equal to 1, 2,